In that case, you see that there are somewhere around this minus 1.7 value in our units of the Jacobi constant. We have the peak of the red part, mainly actually the bar. So the bar is mainly with particles that are in these energies, and with the black part we see the energies of those particles that mainly build the spirals. So having this kind of statistics, we could make our orbital analysis. For instance, in that case, this is the characteristic of the main families we have found. Black is stable, red is unstable, and then minus 1.7 corresponds to this distance here, and x1 is actually, in that case, coming like that. It is not proportional from the center of the galaxy, so most of the bar that is built has energies in that area. So we should model. And what we have found in that case, so here is the isopods of the potential, and here are the stable orbits that we could find. So you see that here we have this x1 orbit. This is one representative of this x1 orbits that is stable, but it just is only inside this kind of, let me call it, bulge, the dark component of the galaxy. Nothing about that. Needless to say that also for this area the majority was not out of the x1 orbits because of their energies. The structure that we have been observed. No islands of stability apart from these retrograde orbits, our bar. Here they are. Here they are. You have seen that we have, as we have seen, so we examined other cases and we could find a single pattern speed with combining two geometries, a flat and a thick geometry that could support the spirals we have seen. Let me go directly to that one. Again, the effective potential is giving us valuable information about what's going to follow, and here is the model that traces very well the spirals. Doesn't do that well with the bar, but we found with the same pattern speed a thicker bar that is much better matching the bar of the galaxy. So, we didn't have good arguments about assuming two pattern speeds. The same procedure. Here are the kind of orbits, however, that seems to give the better result for supporting this kind of spirals in NGC 1300. So many of them, a zoo of them. Okay, I'm going very fast. Here's the other kind of bar that it is again with the same pattern speed, but it is thicker. We get again the answer with a standard mechanism. Here we have nothing peculiar. Order is has enough presence in the models, and here are kind of orbits that support the answer in that case. So, before I finish, I want just to tell you that since we have this nice, maybe what we propose in the paper is that the most possible solution is to get this 16 kilometers per second per kiloparsec value to get the sticky, these polygonal orbits that we found are again chaotic. They are kind of sticky chaotic orbits, as we call them. Again, our interest was focused in the first model, and then we tried to see how the gas responds in that case. We have seen a strong bar was there. The X1 flow that is usually associated with this kind of bars were not present, and we wanted to check how is the gas response in that peculiar case. We used SPH, details if you want I can tell you later, and to our surprise we got the straight dust lane shocks inside the bar of this galaxy. The mechanism does not rely on the presence of the standard X1 flow that we know up to now. Okay, if you let it evolve or if you don't replenish the particles, then you lose the particles in the SPH. The straight dust lane shocks are there. Some figures more on that. Okay, you can. It depends the exact morphology on the abruptness of the introduction of the perturbation. If you do that over several pattern rotations, you have a lot of snapshots that are characterized by that. If you do that more abruptly, you go to this one. And here is how both stellar and gaseous disk are relied. So before finishing, I want just to tell you that already a year now we are studying the comparison in the flows between stars and gas in this type of galaxies, especially where we find that we have chaotic type well, spirals in the stellar component that are supported by chaotic orbits. And I'll show you just a few slides out of that very quickly. It is a work that I do with my student, Evangelia Tsigaridis. And, okay, still on that, like these dust plane shocks are formed by particles that rush from both. This is a kind of chaotic spirals in a model, much more stronger. And actually what we see is that all that we discuss about gaseous flow, and I go very fast to the summary, all kind of mechanisms that I bar with hot orbital population and chaotic spirals. This is the mechanism with the points. Here we have a case with chaotic bar and spirals. Then we have the sticky, I didn't speak about, the slides went very fast through, where ordered structures with 2-pattern speed may give very nice results. The key parameter, we believe that it is the dispersion of the velocities and the difference in the stellar and gaseous flows are what we currently are studying. Thank you.